Alright, well, let's get started. So, today we are talking about the work-energy theorem. The work-energy theorem, we're going to be, first of all, describing work. The work that you do on an object. Now, the work you do on an object is composed of fundamentally two things. Two things make up the work you do on it. Think about this chair for a second, since we can use it. The work I do on the chair is proportional to two things. One, how hard I push on the chair. So the harder I push on the chair, the more work I do on it. And two, how far I move the chair.
So it's position?
How far I move it. It's displacement.
Displacement.
Yes. And work, we can do it in two directions. So I've got this eraser right now. I do work on it to lift it, right? Mm-hmm. And then it does work on me coming back down. And then I do the work, and then it does the work. Or gravity does the work, you could say. Here I'm fighting gravity, and now here gravity's working with me.
Well, not necessarily, because aren't you just lifting your hand down then?
Well, I want it do the work. Is it harder to take a heavy box and put it up on a shelf, or to get the heavy box down off the shelf?
Down.
Right, because gravity's the one doing the work.
Yeah.
Right.
What if you move a chair forward and then back?
So I did work moving it forward, I did work moving it back. So when you're fighting friction, you're always doing work. That's not what we call conservative force. Gravity is a conservative force. I do work putting this marker up here, and then I can let gravity do the work putting it back.
Yeah. But like, is it just when you change directions?
No, it's force times displacement, fundamentally speaking. Here's the most basic intuition. We're going to give you a rough idea of what force is, get more precise, get more precise, get more precise.
Okay.
So in the simplest scenario, when we're just pushing an object, one-dimensional, we'll say there's friction, applying a force in just one dimension, and I displace it, then work is equal to the force I exert on it times the distance I move it. Work equals force times distance. Force has unit of newtons, distance has unit of meters, so it's Newton meters. We have a special name for that, we call that a joule. And it's a measure of energy.
Okay.
So that's work if force and displacement are in the exact same direction. Now that doesn't necessarily have to be the case. So I could be bird's eye view. I'm pushing on a box, but let's say, so here's me, bird's eye view, I'm pushing on a box, but I'm pushing on a box on an angle. So let's say I'm pushing on the box with a force pointing this way. And then we'll say, I don't know, there's some sort of guardrail here, so it can't really go that way. So I'm only moving the box this way.
Okay.
So not all my force is producing work. Only the x component of my force vector in that case is producing work. Does that make sense?
It can only go in the direction of the moving object.
Yes, it's
Okay.
in the direction of the moving object. So this is if the force and displacement are in the exact same direction. If they're in different directions, then work is equal to, think about what it would be. Here's our angle theta.
Mm-hmm.
Here's our force, that vector. What's the magnitude of this thing?
Cosine of theta.
So it's F times cosine theta
Yeah.
times the distance that we actually move it. If we move it, distance d times d. We call that d. Now, going back to your vector notation, your vector math, this is the exact same thing as work is equal to your force vector dotted with your displacement vector. What should we call that? Let's pretend that d here, we'll just call it a vector. So d is your displacement vector, you with me?
Mm-hmm.
So here we were just multiplying by the magnitude of d. Here we do a cross product with the actual d vector. And it's the same thing. Do you remember how to calculate a cross product?
No, I don't.
So a cross product, sorry, not a cross product, that's a dot product.
Dot product.
Yes, the dot product between two vectors.
Isn't that just normal multiplication?
No. Dot product between two vectors is this right here. Here's how you do it.
Oh, okay.
You do the magnitude of this times the magnitude of this times the cosine of the angle between them. That's one way to do it. The other way you can do it is if I say A, vector A is equal to AB, just keep it two-dimensional for now. B is equal to the vector CD. You with me so far?
Mm-hmm.
That is really not a good color. I need to get some markers. Then A dot B, the dot product of the two, is equal to, multiply the x components together, A times C, plus B times D. And notice it just gives you a number. Two products, this is just a number. It's not a
Okay.
vector. That's
Okay.
why it's also called a scalar product, because we get a scalar when it's all said and done. So work is not a vector. Work is a scalar. Work gives us energy, which is a scalar quantity. It is not a vector quantity.
Okay.
Make sense?
Yeah.
Okay. So here's the two ways that we find it. Work is force times the cosine of the angle, force times distance times the cosine of the angle between them, or it's equal to the dot product of the two. Now this is still only the case when force is a constant. When we're talking about a constant force.
A constant force as in just a specific amount of newtons?
I keep pushing with exactly 10 newtons the whole time. It's possible that I start pushing with 10, then push 100, then 10, then 100, and I go back and forth and push it all ski-wampus-y, right?
Yeah.
And my force varies with position. So we'll do that one in a second, but first let's just focus on the case where force is equal to, or where my force is constant. If my force is constant, then my acceleration is constant. And so we can use our constant acceleration equations, right?
Oh, I see. Okay.
So I'm going to see what force times distance equals when I use my acceleration equations. But first, let's look at one of our constant acceleration equations. And I'm going to write it with a little bit different subscripts, but I think you'll know the equation. I'm going to write v2 squared is equal to v1 squared plus 2 times a times the distance you go.
Okay.
You know that equation?
Isn't there time?
Not for this one.
Okay.
The way you've always seen it is times x minus x naught.
Oh.
That's why it's typically written. This is the one you use when you don't have time. Anyways, so I'm just going to put distance there. Same thing, right?
Yeah.
For in the one-dimensional case. Okay, so now I'm going to solve this really quick for a times d. So when I solve for a times d, that gives me a times d is equal to, I need to move this to the other side.
Okay.
And divide by 2.
Yeah.
Okay, so I'm going to have 1/2 v2 squared minus 1/2 v1 squared. You see that?
Mm-hmm.
Yeah.
Okay, so now coming back to work. Work is equal to force times distance is equal to, force can be rewritten as
MA.
mass times acceleration, and then we still have times distance. Times distance is equal to, let's see, I know a times d is equal to this thing, so m times a times d is equal to this thing when I put an m in there.
Yeah.
So it's equal to 1/2 m v2 squared minus 1/2 m v1 squared. Okay, this right here, work energy theorem. Here's it in its simplest case. We'll derive it in a more concrete case. But work is energy, and this work energy theorem states that work is equal to the change in, we call this your kinetic energy. This value, 1/2 mv squared, anytime you see 1/2 mv squared, it's a very famous value in physics. You'll come to know it like the back of your hand. That is, we call that kinetic energy, or sometimes we just represent it with a K for kinetic energy. It is your kinetic energy. Notice that work measures energy, joules,
Yeah.
and so this has the same units. So it's also measuring joules, it's also an energy. And we call it your kinetic energy. It's the energy that you have in your velocity. It's the amount of energy, if we just think about that quantity right there, it's the amount of energy it would take to stop you moving. How much work would I have to do to stop you from moving, or how much energy would I have to exert to stop you from moving?
Okay.
Does that make sense?
Yeah.
So, all my markers are dying. Might have to run to the office. Alright, shoot. Yeah, I'm gonna go get some markers. Stop the recording. Okay. Get back to it. Okay. So we've looked at this in its most simplest case when we're just talking about a constant acceleration, or a constant force, I mean.
Yeah.
Then we see that work, or force times displacement, is equal to 1/2 mv2 squared minus 1/2 mv1 squared. Right?
So basically your V and your V naught.
So if we call this, another way we can say it is that work is equal to, if we call that your kinetic energy at time 2 minus your kinetic energy at time 1, that's another way we can say it,
Okay.
which is one of the ways you'll often see it written. Or you'll see work is just equal to your change in kinetic energy. That's another way you'll see it.
Gotcha.
So a very common thing is you want to know how velocities change with an object. You just calculate the work done on the object, and from that you're able to see the change in kinetic energy, and from that you're able to see a change in velocities. Or vice versa. You know the change in velocities, you're able to figure out the work that was done. So that's it in its simplest case. And we'll come at that now in a slightly more general case. Because now the force might vary from position to position. So let's consider that case, where the force varies. So now, if the force varies from position to position, so sometimes I'm pushing harder, sometimes I'm pushing softer, harder, softer, who knows what's going on. If we were to map your force at each position as you're pushing an object, we'll still assume it's a straight line motion. So your displacement is one-dimensional, but your force keeps varying. You with me?
Yeah.
So this is where the object is, its x position. Here's the force that you're exerting on the object F. And so for the first meter, you know, you might be pushing with a force like this, but then you start pushing with less of a force, then more, then less, then more, etc.
Okay.
You with me so far? Yeah. Now, your work for this little distance right here, for that little teeny distance, for that little delta x right there, is roughly, you can basically assume that you had a constant force of this for that rectangle, right?
Okay.
And so the little delta work that you did in this one little triangle is equal to the force in that little triangle times the delta x in that, or why do I keep saying triangle? Rectangle, right?
Yeah.
And same with for this rectangle. You can make a small rectangle right here and calculate the force the same way. And right here and calculate the force the same way. And right here. And what is the point that we're driving at?
You can just integrate it.
Perfect. We can just say work is equal to the integral from position, we'll say position at A to position at B, whatever those are, two separate points, of your force times your dx.
Times dx.
Yes, because in the integral, remember, as these get arbitrarily small, you replace your delta x with the dx. So what's the area of this? It's the height. I mean, if you want more precise, we say the force at some position x times dx. Here's how you usually see it.
Okay.
Okay, so f of x gives me the height at any x, dx gives me
The width.
my infinitesimal width, right?
Yeah.
So I have a height times a width gives me the area, but it's an infinitesimally small area, and then an integral is an infinite sum.
Mm-hmm.
So I'm summing up those infinitely many, infinitesimally small areas.
Okay.
Good so far?
Yeah.
Okay, now I'm not going to put the f of x there, I'm just going to do f times dx. Same thing though, right? Now, let's think about what we know force is. Force is equal to mass times acceleration.
Okay.
You with me?
Yeah.
And then I also know that velocity is equal to dx dt.
Okay.
Take this and solve for solve for dx. Dx is equal to v times dt. Your velocity over a small interval gives you a small displacement x.
Yeah.
Okay, so I'm now going to make these two substitutions. I'm going to replace f with m dv dt, and I'm going to replace dx with v dt.
Do the DTs get rid of each other then?
Exactly.
Okay.
So this is equal to the integral from, we'll change the bounds here too. Well, we'll keep it a to b. We'll change the bounds in the next one, and you'll see why. But
Okay.
now we have m times dv dt times dx. Right?
Yeah.
And now this is equal to an integral from your velocity at point A to your velocity at point B, because you cancel out the dt's, of m times v times dv.
And m is just a constant.
M is just a constant, perfectly. So when we calculate this integral, what do we get?
And
We have mv squared
mv squared over 2. I'm going to say 1/2 instead of over 2. 1/2 mv squared evaluated from v at A to v at B. Which, once again, is equal to 1/2 mv at point B squared minus 1/2 mv at point A squared.
b and point
Oh. Same thing. Same formula just popped up. I told you we're going to show that this keeps holding in more and more general situations.
A. I see.
So we showed it in the simplest case where you just are pushing in one dimension, one-dimensional displacement,
Okay.
and you have a constant force. Now we said even if your force is varying, this still happens to be the case. Now the last case that we need to handle is, okay, let's show that this still works even when we're talking about three-dimensional displacement.
Okay.
So, once again, I know now my work in 3 dimensions is equal to the integral from point A to point B, but now this is no longer straight line motion from A to B. A could be a point right here, and B could be a point right here.
Yeah.
And our path in between could be some awkward, weird thing.
Yeah.
So we're talking about some random path, who knows, in 3 dimensions from some point A to some point B. Completely arbitrary.
Okay.
Okay, our work then is going to be the cross product of our force vector with our displacement vector. I'll use dr.
Your vectors. Okay.
Yes, we're talking about vectors now, and we're using a dot product.
Why dr?
That's our position vector. Remember, dx is just a component of dr. What is dr? Remind ourselves of dr again. Dr, the vector dr, is equal to dx, comma dy, comma dz.
Oh, that's right. Okay.
Does that make sense? And f here, we're going to assume f is just equal to the component of your force in the x direction, the component of your force in the y direction, the component of your force in the z direction. Make sense?
Yeah.
Why do you multiply by dr?
I'm doing the exact same thing we did up here, just 3 dimensions. A small force dotted with dr across a very small distance gives us a very small amount of change in work. Add up all those changes in work. Gives us a total change in work.
Yeah.
Make sense?
Yeah.
Okay. I don't know how much this is going to blow up. Let me try and write it a little bit more compact. Okay, so this is equal to, we're just going to take that dot product. You with me?
Yep.
So how do you take a dot product? You take the x times the x, the y times the y, the z times the z, and you add them all up.
Okay.
And I'm going to put each of those in their own integral. The integral of the sum is the sum of the integrals.
Yeah.
Okay, so this is the same thing as the integral from a to b of f of x times dx, write that one first, Notice now that these are scalar quantities. These aren't vectors anymore. They were components of a vector. They're just numbers.
Okay.
Okay. Plus the integral from a to b of f of y dy plus the integral from a to b of f of z dz. But now we know how to calculate each of these integrals.
Yeah, we do.
We just did it right here.
But it's a bunch of those.
Right, for all our different cases, but the point is, up here we were just using a number and a number. Now we've reduced these to numbers and numbers, and so we know what we get there.
Just a number.
Just the change in velocities. We get this. Here's what we get.
Okay.
So in other words, this is equal to, when I calculate this integral, what am I going to get? I'm going to get 1/2 m vb in the x direction squared minus 1/2 m my velocity at a in the x direction squared. That was calculating the first integral.
Yeah, and then you do the same thing.
With me?
Yeah.
And then same thing for the y's. So plus 1/2 m my velocity at point B in the y direction squared minus 1/2 m my velocity at A in the y direction squared plus 1/2 m my velocity at B in the z direction squared minus 1/2 m my velocity at A in the z direction squared. Good so far?
Yeah.
Okay, so I'm going to factor, first of all, I'm going to factor the 1/2 m out of everything.
Okay.
1/2 m. And then I'm going to write all my VB, my velocities at point B first. And then I'll do my velocities at point A. So my velocities at point B, I have a positive VB in the x direction squared plus VB in the y direction squared plus VB in the z direction squared. And then we have minus VA in the x direction squared minus VA in the y direction squared minus VA in the z direction squared.
Yeah.
Yeah.
Okay. Shoot, I should have written it like this. I'm going to say a minus here, and then put some more parentheses around all these and make that a sum.
Okay.
With me? Okay, so what is VB in the x direction squared plus VB in the y direction squared plus VB in the z direction squared?
Just the vector, maybe.
It's the magnitude of that vector, VB squared. That is VB squared.
How is it the
Not
magnitude? It's not a vector?
You can't multiply a bunch of numbers together and get a vector.
But aren't those positions in space?
That's your velocity in the x direction at point B.
Yeah, plus your velocity in the y.
Sorry, the magnitude of your velocity. It's your speed in the x direction at B.
Speed is magnitude?
Okay. How am I losing you so much? Just looking at BBX. Look, my velocity at B is a vector. Velocity is a vector, right?
Yes.
And it has three components, if we're in 3 dimensions. You have my velocity in the x direction, so VB sub x, comma. You have my velocity in the y direction, VB sub y, comma. And you have my velocity in the z direction, VB sub z. This is a vector, these are just numbers.
Mm-hmm.
This tells me how fast I'm going in the x direction, how fast I'm going in the y direction, how fast I'm going in the z direction.
Yes. Yes.
Okay, so they're just speeds now.
Mm-hmm.
Okay.
Good? So that's all this is that number squared.
Yes, so how is that the magnitude of it?
No. These three added together. So look at this vector for a second. Let's start with the 2-dimensional vector. Maybe you're getting a little thrown off here. So let's just put this problem on hold for a second and just think about velocity vector is equal to v1, comma v2. or Vx comma Vy. Right?
Mm-hmm.
Let's find the magnitude now of V. How long is it? Let's get a picture of this vector. Whatever it does, it goes over this way and up this way. This distance is Vx, this distance is Vy.
Okay.
You with me?
Yep.
What's the magnitude of V now?
Which is Vx squared plus Vy squared rooted 12.
Yes, the magnitude of V now, the magnitude of our vector, sorry, this was a vector, that's a vector. The magnitude of V is equal to the square root of Vx squared plus Vy squared. Pythagorean theorem,
Yeah.
right? If it were a three-dimensional vector, all that changes is plus Vz squared.
Okay.
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 I see it now.
This is the magnitude of this vector squared.
Okay.
So this whole quantity right here, so this is equal to, now we gotta erase some of this. This whole thing right here is equal to, we'll keep the 1/2 m real quick, is equal to the magnitude of VB squared. That's what this plus this is equal to.
Why doesn't it just remake the vector? Because you have all the components you need.
You can't add and multiply numbers together to get a vector.
But you have the speed at x, the speed at y, and the speed at z.
We could figure out the vector that goes along with this, but there's no algebraic operation, take numbers and turn it into vector.
But you can take vectors and turn them into numbers.
We do that all the time. We take the magnitude of a vector, which gives us a scalar. We take the dot product of two vectors, that gives us a scalar. There's no operation that says, here's two numbers, now turn them into a vector with this operation.
But you have your vector equals those three speeds.
You're saying here?
Yeah.
Whoa, whoa, whoa. My vector is equal to an ordered collection of those three numbers.
And you have those other.
It's not equal to the sum of them. It's not equal to the product of them.
Oh.
It's not equal to some algebraic manipulation of them. This is a data structure.
Okay, that makes sense.
Okay, yes. Good. So, making sense now? We
Yeah.
got rid of vectors when we went from here to here. Going from here to here, there's no more vectors. And we got all our vectors out. That's what we always do with vectors. We take vectors and we say, I don't want to work with vectors. I want to just work with real numbers. And so we break it into its components. We say, what's it doing in the x direction? What's it doing in the y direction?
Okay.
Which is what we did. We took this integral and we turned it into three integrals, one in the x direction, one in the y direction, one in the z direction. Because we know how to work with those real easily. Vectors, we hate working with. Make sense? Okay. So, you add up those three, and you get the velocity of v squared. When you add up these three, you get
Velocity
the...
of a squared.
Yeah, should say the magnitude of the velocity at a squared. Make sure that it's clear that we're not talking about vectors. V squared at a, which is the same thing now as 1/2 m velocity at b squared minus 1/2 m velocity at a squared.
Yep.
Same thing.
Yep.
So, no matter what, work is equal to this quantity, your change in kinetic energy when you add up all the work being done. And this is the total work. So this force here is the sum of all your force vectors acting on the object. That's important to understand. You can't just pick one force and add that up. So for example, if we want the change in kinetic energy from me sliding a box, you have to take into account two things. You have to take into account my pushing the box, that's one force acting on it. You have to take into account friction, you have to take into account its weight, and you have to take into account the normal force. Add all those up, that's what this F is.
I see.
Make sense? This is a sum of all your forces. And so your total work is what that's equal to. If you just calculate the work of my pushing the box, that's not necessarily going to come out this way. You have to count for all the forces acting on the box. And when you calculate the work all those forces do on the box, then that's what comes out. Because obviously, when we're talking about sliding the box, I'm going to do way more work than actually goes into its velocity. Because I have to overcome friction. Because friction is doing work in the opposite direction.
Yeah.
And so those two kind of cancel each other out. Give you just an intuitive example. Imagine I'm taking a box and I'm pushing it with constant velocity. So I'm pushing it exactly as hard as kinetic friction is pushing back.
Okay.
I am doing work on the box because I'm applying a force, the same as kinetic friction. Kinetic friction is also applying a force on the box, the same as me. And so the net work being done on the box is 0. And so its speed doesn't change. Then if you took me to outer space, where there is no friction, and I somehow am pushing the box forward and doing work on the box, now that box is going to speed up as long as I'm doing work on it.
Yeah.
Because I'm the only one doing work on it. And so it's going to speed up exactly how this equation predicts. So this F right here is the sum of all your force vectors. Your net force vector.
Can you find it for this part?
You can find the work done by one force, then the other, and then add up all those works. And then this equation will hold. So this is your total work. Needs to be the total work done on the object. Good?
And so things like friction do work?
Yes. Every force acting on an object that's being displaced does work.
It's being displaced.
As long as it's moving. If the object's not moving, no work's being done.
So what if you just push on something?
I'm pushing on this. I am not doing any work on this wall.
Yeah, that makes sense.
I'm holding this book up. I am not doing any work on this book. Now you'll think, I'm actually going to get really tired holding up this book. Getting tired and doing work are not the same thing.
It's true.
I'm not doing any work on the book, but my muscles get more and more tired.
Why is that?
Human body's a lot more complex. Technically, my muscles are doing work because they're expanding and contracting, And so there's a lot of displacement internally inside of me that's going on. But obviously, we're not going to be able to take that into account when we're talking about your first run through at how much work you do.
Okay.
That would be pretty advanced, trying to figure out how much work your muscle. I think it would. I don't know how to do it, but maybe it's simple and I just don't know how to do it. Okay. One special case that we are very interested in has to do with, should we introduce springs yet? Or should we just do a bunch of examples first and then do springs?
I think we should do some examples first.
Okay, so here's the two things I still need to talk about, don't let me forget. We still need to talk about springs. And then we need to talk about power. And we'll be done. Power, yeah. Power, I mean intuitively, it's already easy. What's power? It's the derivative of work with respect to time. It's a change in work. It's a change in energy. It's watts. It's joules per second.
Joules per second.
Yeah.
Watts. That's
Watts.
what watt is?
Yes, how much energy per second it's using.
That's cool.
Yeah. So we'll do a little bit more in depth in those, but let's just jump into a bunch of example problems now, using just work and work energy. But yes, this is an extremely useful theorem because, well, we probably won't see a lot of the use cases with it until the next chapter. But there's a lot of times where you want to know how fast would an object that's fallen so far, if I take this object, how fast is it going after it's dropped a meter? We use like the work energy theorem to calculate that really quickly, as opposed to using all our equations that we used before.
That makes sense.
Okay, let's see our first example. Steve exerts a steady force of 210 newtons on a stalled car at an angle of 30 degrees. Okay, so we've got a stalled car here. Steve is pushing on it. Bird's eye view, Steve's pushing on it on an angle. The car is going to go forward, and I think our displacement here is 20 meters. I think I saw that number in the corner of my eye. 18 meters. 18 meters. And our question is going to be, how much work does he do on the car?
Is he going 30 degrees to the side or 30 degrees up?
30 degrees to side. Bird's eye view.
That's weird.
They rationalize it. One of the tires are flat, so pushing it at a 30-degree angle helps keep it going straight, blah, blah, blah.
Okay.
Doesn't matter. Okay, so looking at Steve now, let's draw his, draw the force vector, I guess. Nothing else to do. So here's our force vector that Steve is applying, and he's applying it at an angle of 30 degrees. He's pushing with a force vector with magnitude 210 newtons. So the length of that is 210 newtons. Our job is to calculate the work that Steve has done on the car. What do we need to do? We need to find the component in the x direction, and then we just multiply it by the displacement.
That's easy.
So it's just the f in the x direction times the displacement that we do. I don't know, maybe you want delta x there, whatever you like.
Which is just the cosine.
And so that's going to be 210 times the cosine of 30 degrees, which is
Root 3
One.
over 2.
root 3 over 2.
Oh.
Don't do it from the top of the circle. Times
Times the 18.
times 18. Perfect. So 2 cancels out with 18, making 9 of those. What's 9 times 210? 9 times 21 might be an easier way for you to think about it. What's 9 times 2?
9 times 2.
Yeah, sure, start there.
9 times 2 is
What's
just
9 times 200 if you'd rather?
18,000.
1800. And then what's 9 times 10?
90.
90. There you go. Root 3. Don't forget my root 3.
Oh, that's.
Which is going to come out to however many newtons. I haven't pulled out my calculator yet, so I can't find it.
Naturally.
Huh?
Naturally.
Gee, as we get your calculators, you could do your job.
It'd be kind of neat.
Your job is to plug in these numbers for me so I don't have to.
Pretty good practice.
And how many significant figures do we have? Just 2 significant figures. And so we've got roughly 3.3 times 10 to the 3 joules. 3.3 times 10 to the 3 joules. What do you got? Oh, there's part B. Okay, part A, yes, we got it. Part B. In a helpful mood, Steve pushes a second stalled car with a steady force of F equal to, they use the IJ notation, but I just write it this way, I think it's cleaner.
Okay.
Equal to 160 and minus 40. And he displaces it by a vector 14 meters, 11 meters. So the displacement vector, I guess we'll use S, should say do, is equal to 14 meters and 11 meters. So now how much work does he do? Now you can hit your life if you want. And you can come and you can try and draw this whole thing out. Let's see, he goes 160 over and 40 down, so that's a force vector like that, kind of. And then the displacement vectors, 14 over and 11 up, okay. And then you can try and find the angle between them.
How do you find the angle between them?
You'd have to find the angle that this one makes, find the angle that this one makes, add the angles together using arctangent. And you can make this all one big nightmare of a problem. Or you can remember that we can say that work is equal to force times, they're using S for displacement, so we'll do that. Or force times cosine of theta times S. Or it's equal to, another way to get the exact same quantity is the force vector dotted with the displacement vector. So we're just going to take the dot product of these and not hate our lives.
Okay.
You could do it that way. There's nothing wrong with doing it that way, except for it's a lot more algebra. Whereas if we just take the dot product of these two, then we see that work is equal to F dotted with S is equal to 160 times 14 minus 440. And now we can plug that in. You understand how I took the dot product, right?
Yeah.
Yep.
And we get 1,800. Good.
Why do you convert it to that instead of just saying 1800 joules?
Scientific notation. Just common practice for when you start dealing with bigger numbers.
Okay.
It's just cleaner, easier to read, easier to understand. Because, I mean, there comes a point where you're dealing with big numbers and you're like, how many zeros is that? Why don't you just tell them? Make it real easy. You see that these two numbers are basically the same order of magnitude. If I multiply these two numbers together, I know it's 3.3 times 1.8, now with 6 zeros behind it.
Yeah.
Well, not 6 zeros, but shifted 6 places. Okay. Let's see. Next one. A farmer hitches up his tractor with a load of firewood, pulls a distance of 20 meters. Got the weight. All right. I'm guessing he's pulling at some angle. So we've got some sled here full of firewood being pulled that way by some tractor. So hitched up to some tractor right there that I'm not going to try and draw.
Okay.
And it's going to be displaced 20 meters. Let's see. The angle is 36.9. So our angle here is 36.9 degrees. The pull of the tractor is pulling with 5,000 newtons. And let's see. Friction is pulling it back with 3,500 newtons. And we've got the weight of the sled is 14,700. The weight of the sled is 14,700. Okay, let's draw our free body diagram over here real quick. So we've got the force of friction this way. We've got, I'll just call it the tension from the tractor. You good with that?
Yeah.
It'll probably be our only F. We can probably just call it capital F. Nah, let's keep the tension. So I can use F for the total of all forces. And then we're going to have the weight pulling down, and then we're going to have the normal force perfectly canceling out the weight, pushing up. Not perfectly canceling out, I'm sorry. Because this is also pulling up some.
Yeah.
And the slave's not moving up. So we're going to have, that was 36.9 degrees. Then this we'll call T sub x, and this we'll call T sub y. Right? Okay. Okay. So, what exactly was our job? Find the work done by each force acting on the sled, and then the total work done by all the forces. So, first off, what's the work done by the normal force?
That's the weight minus the tension and y.
How much work does a normal force do on the sled as the sled slides this way 20 meters?
0.
0. The normal force does not displace it in this direction any.
All the work.
The work done, yes.
Yeah.
And what's the work done by gravity, by its weight?
Also 0.
Also 0. So weight and normal force don't factor into this. They do no work.
How about your friction?
We don't
It's
need
not
it.
moving this way.
Friction is going in the opposite direction.
Of your movement.
Okay, so work, our definition really quick. Work was equal to the magnitude of your force times the cosine of the angle between them times
Your distance.
your distance, right?
Yeah.
If force is, or friction is pushing that way, what's the angle there?
0.
180.
180.
180, sorry.
What's cosine of 180?
-1.
-1, not 0. What's cosine at 90?
That's 0.
What's cosine at 270?
0.
Okay.
So this is doing work. It's doing work in the opposite direction.
Even
It's
though
doing
it's not
negative
being
work.
moved,
It is being moved.
but not in this direction.
Which is why it's a negative.
It's being moved in that coordinate system. It's just negative work.
Negative work.
Negative work.
Yes, negative work. It is opposing the work being done. Think about it this way. You and Jeremy are both pushing a box. You're pushing it that way, Jeremy's pushing it this way. You're both pushing the exact same hard on a completely frictionless surface, but the box happens to be going that way 1 meter per second. So now you're both sliding 1 meter per second.
Yeah.
Your work has to be perfectly canceling out his work because the total work is 0. Because the velocity is not changing. Work energy theorem. Work produces changes in velocity.
Changes in. Okay.
Work is equal to the change in the total work is equal to the change in kinetic energy, which has velocity in it. If your velocity doesn't change, your kinetic energy doesn't change. If your kinetic energy doesn't change, you didn't do any total work. You're obviously doing work since you're pushing the box and it's being displaced.
Yeah.
So your work must be being canceled out somehow because the box isn't speeding up. So there must be negative work,
Okay. That makes sense.
which is Jeremy pushing back on you. The jerk won't let you go. Can't say jerk because that's the derivative of acceleration. And there is no jerk. There's not even acceleration. It's constant velocity. So there's no jerk. So Jeremy must not be a jerk because he's there.
Oh my god.
And that's just demonstrated.
There you go. All right, so now let's calculate the work of friction. The work done by friction, then, is equal to the magnitude times the cosine of the angle times s, times the displacement. So obviously the cosine is just going to give us our negative sign, which is good. We expect friction to do negative work.
So it's negative.
So 35 times 20, which is 7,000, right?
Yeah.
Guess we'll write it out. Okay, finally we need to calculate the work done by
No.
the tension.
Isn't that 70,000?
Oh, did I screw it up? Yep, thank you.
Okay.
Okay, now we have this force, the work done by tension. Now only the work in the x direction factors into this one,
Because the y is being canceled out. Because it's not.
because the y isn't doing any work.
Yeah.
Only the x component is doing work. So this one's going to be t sub x times s, right?
Mhm.
Okay, so now t sub x is equal to 5,000 times the cosine of 36.9 degrees, right?
Yeah.
So calculate that, multiply it by 20, and that gives us our total work. So we have 5, 1, 2, 3 times cosine of 36.9 times 20 is equal to about 80,000. So this comes out to about 8.0 times 10 to the 4 newtons. They just say 70 kilojoules, same thing. Kilojoules.
Kilograms.
Oh, not newtons. This is joules. Can't believe you guys let me write that. Joules. We're talking about energy. Yeah. So rather than that, they say this is also the same thing as negative 70 kilojoules. K stands for 1,000.
Mhm.
Or, for example, when we measure how much energy you use, and it's a weird one, we call it kilowatt hours, which is an energy, not a power. We'll make that when it makes sense
Like
after.
light year? Oh, it's distance, not time.
A light year is distance. And the one that kills me when everyone always talks about a quantum leap. There's always some great big distance, and the quantum leap is like from here to there.
Really?
Those are a quantum leap apart.
Okay.
You have heard that. There's no way you haven't heard it.
Yeah.
You're
People
saying
say it all
like
the
in
time.
movies or something?
People in regular speech, when they try to say that they're really, really far apart, they often say,
That's a quantum leap.
yeah, those two are a quantum leap apart.
Okay.
Yeah, he's been gone for like a light year.
Yeah. It's gonna take light years for that to happen.
Okay. Anyways,
So what's the total work then?
oh, the total work. So now work total. What's work total?
Just like 1 kilojoule.
10 kilojoules.
Oh, that's right.
80 minus 70 is
10,000.
okay. That covers that example problem. On to the next one. Or do we have any questions?
It makes sense, but yeah, let's do another one.
Why can't the homework problems be like these?
They are.
They are,
Not.
like, I think we did every single homework problem in class. I just forgot it all.
Yeah, I should probably record those and put them in a place where you have access to them.
I looked online, but you didn't upload it, so
It's
it's
still
like,
up.
I'll get help tomorrow.
Yeah, and our internet, I don't think it's working here, so it might not even be uploaded by the end of class, unfortunately. Okay, let's look again at the sled from what I just erased. Oh, the sled in figure 6.7. Is that what I erased?
No, you erased, yes.
Are there multiple sleds?
I don't know, this is like a picture book. So many pictures. And our results from example 6.2, yes, that's what we just erased. Suppose the sled's initial speed is 2 meters per second. What is the speed after the sled moves 20 meters? Okay, so same picture before. So we had our sled, right?
Yeah.
And we moved it 20 meters. Here, it has a velocity, we'll call it v1, equal to 2 meters per second. Question is, what is the velocity here now? Now remember, we calculated the total work already, so we don't need to go through that. The total work was equal to what?
10 kilojoules.
10 kilojoules. 10,000, if we want to write it out, 10,000 joules.
Okay.
Right? Now, that's the total work, the work energy theorem. That's also a change in kinetic energy, which means my kinetic energy here minus my kinetic energy here has to equal 10,000.
Yeah.
So what's my kinetic energy here? That's 1/2 mv2 squared. What's my kinetic energy here? That's 1/2 mv1 squared. Now, what's the big thing that we're missing in that equation?
Your mass.
Our mass. So we need to get our mass. We have to go back to that stupid problem and refine the weight. The weight was 1470. So the weight of the sled
14
was 14,700 newtons, right?
Mm-hmm.
And so its mass is equal to 1470 over g, right?
Yes, sir.
Yeah.
So we now have its mass. We're trying to solve for V2. Let's really quick rework this equation in terms of V2. So I know that 1/2 mv2 squared is equal to, I'll just put work total, which we know is 10,000, plus 1/2 mv1 squared, right?
Yeah.
Yeah.
Okay? Multiply by 2 and divide by m, so we get v2 squared is equal to 2 times work total over m plus v1 squared.
divided by 1/2.
Multiply both sides by 2, and then divide both sides by m.
Okay.
So now you square root the whole thing?
So now square root the whole thing. So v2 is equal to plus or minus square root. Obviously, we're just going to have a positive case. Of 2 times our work total work divided by m plus v1.
V1 is just 2.
And v1 is just 2. So we'll plug in numbers now. So I am looking for the square root of 2 times 10,000 times, or divided by our mass.
700 divided by G.
And our mass is 14700 divided by 9.8. Okay. Plus
2.
2 squared. That should be squared. Right?
Oh, yeah.
And we get 4.2 roughly. So that should have been squared. It comes out to 4.2 meters per second.
Is there just one significant figure or 2?
I'm guessing there's 2. Looking at the problem, that has 3 significant figures, that has 3. That only has 2.
Velocity was just 2.
So it comes out just 2 significant figures. So 4.2. Yep, we got right. Next example. A steel hammerhead of a pile driver is lifted 3 meters above the top of a vertical I-beam, being driven into the ground. The hammerhead is then dropped, driving the I-beam 7.4 centimeters deep into the ground. The vertical guide rails exert a constant 60 Newton friction force on the hammerhead. Use the work energy theorem to find A, the speed of the hammerhead just as it hits the I-beam, and B, the average force of the hammerhead exerted on the I-beam. Ignore the effects of air.
Average force.
So,
Why do they call it hammerhead? This is how much it's sharp.
huh?
Why would you say hammer?
No, it's an actual piece of equipment.
A hammerhead? What's the difference?
So it's like a big piece of metal that you lift into the air with a machine and then suddenly drop it. You lift into the air and drop it.
So it's
A
kind
big
of
piece of metal comes and it has a part on it like that to pound. So a big honking piece of metal like that. We're lifting it up and dropping it onto an I-beam to pound the I-beam into the ground, and there's some guide rails to make sure it actually hits the I-beam that we want to hit. So it's going to hit our I-beam here. Here's our I-beam that we're pounding. We drop it 3 meters here. It falls, pounds on the I-beam. When it pounds on the I-beam, it only moves it into the ground 7.4 centimeters or something like that. 7.4 centimeters. So 0.074 in terms of meters is how much it shifts.
Kind of good.
So that's physically what's happening. Let's draw our free body diagram for the hammerhead. For the hammerhead, we have its weight pulling it down, and then we have kinetic friction pushing back up on it.
Kinetic friction from the guide rails?
From the guide rails.
Okay.
Yeah. So it's going to fall. This is the instant we let it go. So no more normal force, so it's just falling. The guide rails are creating a little bit of friction, and then its weight is pulling it down.
Okay.
Right?
Do we know
Yes.
how much friction?
Yeah, they told us 60 newtons. So I know F sub K is equal to 60 newtons.
Did it say
And I
60
know
newtons to each side or just
the
60
mass,
total?
just total. And I know the mass of this thing, I think, is 200 kilograms.
200 kilograms.
Yeah.
Okay.
So let's calculate the work done. So then the work, or total work, is equal to our force, the work that this thing does. What's the work gravity does? Let's look at the work of gravity.
Okay.
The work of gravity is just going to be weight times displacement.
Weight times
Are
displacement.
you looking at the weight total or the weight of just the gravity? Because there's also friction.
Well, and then we need a minus the work done by friction, which is
60 newtons
60 times 3.
times 3, yeah.
So 60 times 3 is 180 joules.
Oh, you're just doing it all at once.
So is the
I'm calculating the total work. The work, and this is W as in weight, sorry, not work.
is the newtons per meter? Or why do you multiply by 3?
That's the displacement.
Displacement.
Force times displacement, where W is equal to mg.
Oh,
Yeah, sorry.
But then
Maybe
you're going
a little
force
better
times
chance.
displacement minus force times displacement.
yeah, because it's just adding up all
I'm doing the total work.
the works.
Here's the work done by gravity.
Okay?
Here's the work done by friction.
He just skips.
Oh, so instead of just finding F, then you just put it all in. If that makes sense.
Yeah.
You could do it that way if you wanted. I mean,
It makes more sense to me.
okay, so we'll do it that way. So we'll say we have mg minus f sub k times 3 our displacement.
There you go.
Okay. So this is equal to, now some number. Who cares what the number is for now? But it's also equal to the change in kinetic energy,
Okay?
right? Remember, what we're trying to find is a velocity that this hits this with. That's
The
what we're after.
speed, right?
The speed, yeah.
Okay.
So this is also equal to 1/2 mv naught squared plus 1/2 mv, we'll say 1 squared.
Which one is when it ends?
Oops.
Why are you adding?
Sorry. 1 minus start.
Okay, and the start is still 0, right?
The start is 0. It doesn't have any velocity to begin with. So it has 0 kinetic energy in the start. So this whole term is gone.
Oh, that's easy.
So the amount of work done is the total kinetic energy it has at the end.
Okay?
Because it has no kinetic energy at the start, we did some work on it, so now it has some kinetic energy. And all the work, the total work produces the change in kinetic energy or the kinetic energy it has. Make sense?
Mm-hmm.
Yeah.
Okay? We're looking for
V1.
V1. So V1 then, V1 squared is equal to, multiply both sides by 2, so you're going to turn that 3 into 6. And then we'll have to divide by m. So 6 divided by m times mg minus f sub k.
Do the M's cancel out?
You can if you want, so we can rewrite this as a, distribute that m inside, we can call this 6g minus f sub k over m.
Wouldn't it be multiplying F sub K?
Multiplying f sub k by 1 over m.
Mm-hmm.
Oh, yeah.
So, then v1 is going to be square root of that. Of 6 times g minus f sub k over n. Figure out what that is, and that will be our velocity. So we have 6 times, oops, forgot my square root. Square root of 6 times 9.8 minus 60 divided by 200, right?
Mm-hmm.
And we get 7.55.
7.55 meters a second.
Yep, let's see, 7.55, same thing they got. .55 meters per second. So that was part A of the problem. Part B asks us to find the average force the hammerhead exerts on the I-beam. Ignore the effects of the air. Okay, so now for the second part of the problem is when this thing makes contact with that I-beam,
Okay.
right? So let's put V1 equals 7.55 meters per second, and then we can erase this. Well, we probably have enough room to work with anyways. So, free body diagram now for the second part. for this I-beam here getting pounded by that hammerhead. So it's getting pounded by the hammerhead. So this is going to be the weight of the hammerhead, right?
Mm-hmm.
Are you gonna include the weight?
Maybe we'll just still look at the hammerhead. We'll look at this. We'll think about the tip of that thing right there. Free body diagram there. So that's going to pound on that I-beam. So there's going to be a massive normal force slowing this thing down, right?
What's going on?
You're going to draw a free body diagram for the hammerhead as it hits the I-beam now. So we did the free body diagram when it's in free fall.
Yeah.
Now we're doing the free body diagram for this thing when it hits the I-beam.
So the moment it touches it?
The instant it touches it, and now we're looking at from the instant it touches it until this I-beam shifts 7.4 centimeters into the ground.
So why do you
now
have
we're talking
normal force then?
This is hitting the I-beam.
Oh.
That's producing a huge normal force. That was the whole point of this, right?
Okay. Yes.
So, normal force, work, and then we also have, or its weight, and then we also have pointing up as well, we still have kinetic friction.
What about the weight of the I-beam?
The weight of the I-beam doesn't factor into the free body diagram of this thing,
Okay.
because its weight together with everything else, how hard the dirt is under it and all that, is factored in. That all comes into account by the fact that this thing only shifts 7.4 centimeters. So the fact that this only shifts 7.4 centimeters is taking that all into account.
Okay.
Because obviously if the I-beam, for example, had infinite mass, this whacking it wouldn't shift it.
Yeah.
So how much it shifts, already taking that into account. Okay, so here's our new free body diagram. Okay, so let's once again find the total work. We're after the normal force here, by the way, I think. I think that's what we're after. So we're trying to calculate now this normal force. Okay? So I know that the total work is equal to the normal force plus the force of friction plus the weight.
Minus the weight.
We can think about that way if you want, yep. Minus the weight. Maybe we'll be fine. Okay, normal force plus force of friction minus the weight times
3. Or 0.074.
times, we'll just leave that in as a, what should we call that? I don't want to write that number over and over again.
Distance.
We'll just call it a small h. Times the height that gets displaced. This is also equal to our change in kinetic energy.
Okay.
Yeah, I should do this way to be consistent. So it's going to be weight minus the force of kinetic friction minus the normal force. To stay consistent, because up there, we called the downward direction positive. And we're still calling the downward direction positive.
So we're
calling
going to
that
end up
positive
with a
displacement.
negative?
No.
Aren't we
Oh, the
looking for
force,
normal
the normal force is in the negative direction. Yes.
Okay.
Okay. So, there's our total work, right?
Yeah.
Just force times displacement, adding up all the forces. This is equal to the change in kinetic energy. So it's equal to our ending velocity, 1/2 m, I'll call it v2 squared, minus 1/2 m v1 squared. Where v1 was the velocity it had right when it hit the thing, right?
Mm-hmm.
And v2 is the velocity it has when this thing stops moving. So what's v2?
0.
0. So it's equal to negative 1/2 mv1 squared. You follow that?
Yeah.
Okay. So let me erase the work total here now. We don't need that anymore. We're just using this equation. And now I'm just using this equation to solve for the normal force.
So just plug everything in.
Because you know everything but
Right. So I know that negative my normal force times h, well, we'll shift it to the other side. I'm going to shift my normal force over here and this value over here. Okay? So we're going to have weight times h. Maybe I'll plug in mg there just so we don't get confused with any work. Mg times h minus f sub k times h plus 1/2 mv1 squared is equal to normal force times h. Okay? Follow my thinking there? So finally, our normal force then is just equal to this whole sum divided by h. So it's equal to m times g minus f sub k. I'm just dividing everything by h.
Yep.
Plus 1 over 2h m. Excuse me. 1 over 2h m v1 squared.
Okay.
So my normal force then is, let's see, 200 times 9.8 minus 60 plus 1 divided by 2 times h, which is 0.074. Times the mass, which is 200, times our velocity squared, 78900. Check here. Oh, they just have two decimal places. They just have 79. 79,000. 79,000 newtons. So that's the average force that that hammerhead exerts on that I-beam.
Average force?
The average force.
Average force is equal to normal force?
Well, we assumed that normal force was constant. I mean, really, if we graphed the normal force over time, it could have looked like this.
Yeah.
We just barely assumed it was constant. And so the average is what we did.
Okay.
That was built into our assumption because we treated the normal force as just n, some constant throughout the entire change. Which is what I asked for, so the average force that it exerts. So there you go. Just for a point of interest, let's do 79000, the average force it exerts, divided by its weight. So it exerts a force of 40 times its weight onto the I-beam during that interval.
During that interval.
Mm-hmm.
Dang, that's a lot of force.
Yeah, good amount of force. Hammers work well. Okay, so now we're to the point in the book where we talk about springs. So let's talk about springs. Springs are fun. Springs, crucial to understand them because we use springs a lot in physics. Once we get to harmonic motion, we'll be using springs a ton. And so there's a famous law dealing with springs called Hooke's law to calculate the force that a spring exerts on an object. You know from experience that the more you stretch a spring, the more it wants to pull back.
Mm-hmm.
And so how hard a spring pulls is proportional to how much you displace it. So if I've got a wall right here, some spring sticking out of the wall, and we're pulling on it this way with some force F. Let's say the spring, when we're not exerting a force on it, is naturally right here. So we'll call this x equal to 0.
Okay.
we're pulling the spring out some distance, so it's now at some position x1. So we've displaced it some delta x. It turns out that the force is proportional to this displacement. How do they represent the displacement in the book? They just call it x. So if we call that x equal to 0, then this is just your x position from there on out, right?
Yeah.
So set up our coordinate system so that this is x equal to 0, your displacement then. So it's just proportional to x, which means it's some constant times x, where that constant depends upon the spring you're using. A slinky has a really small k value,
Yeah.
and so it's a really small force. A trampoline spring has a really big k value. It's really hard to pull that thing out.
Yeah.
And if your spring has space between the coils when you let it go, then the force goes both ways. So compressing it is the same as pulling it apart. They're both proportional to the displacement. And it's roughly as hard to compress a spring a foot as it is to stretch it a foot, if there's space between the coils when it's at its regular length. Obviously, like a trampoline spring, you can't compress
Yeah.
because the mouth's touching each other.
Okay.
But you can think about if we hung a slinky from the ceiling, so now it's stretched out, it's just as hard to pull it down a foot as it is to push it up a foot. Kind of. The weight comes into the picture there. That's not a good example. Just if you had spring that was already stretched out.
Okay.
Okay, and this is called Hooke's law. Now, Hooke's law only holds as an approximation if you're not doing crazy things with the spring. Obviously, I could take a trampoline spring, and I could, if I have an insane amount of force, I could pull it straight. So now it's just a straight wire. It's not a spring anymore. It's been deformed.
Yeah.
And it no longer obeys Hooke's law. Because when I let go, it's not going to recoil. There's no
So
force
it has
anymore.
to be a spring.
It has to be a spring, but you can't deform the spring, for one. You can't bend the spring. It's real easy to bend a slinky straight, right?
Yeah.
And it's not a spring anymore. So it only works within limits. You can't apply extreme forces. It works within limits. It's just a good approximation for a lot of day-to-day springs.
Yeah.
Make sense? Okay, so one of the things we're naturally interested in then is how much work you have to do to stretch a spring some amount.
Okay.
So let's calculate the work. So if you are going to stretch a spring some distance from x1 to x2 now, whatever it is, how are we going to calculate that?
You take your total displacement and you multiply it by the force.
So Hooke's law follows this. So if we model your force with respect to x, it's going to look something like this. So here's x equal to 0 where the slinky isn't. First off, here's the x direction. Here's your force direction. Good?
Yeah.
Okay. So now, your spring, when it's at rest, is right here, so there's no force. If I start pulling the spring out, I need more and more force. Right?
Okay.
If I start pushing the spring in, I need more and more force in the opposite direction.
I see.
So if I stretch a spring from some position x1 to some position x2, how do we calculate the work done by it?
The displacement difference in kinetic energy. Right?
No, we don't need to think about in terms of kinetic energy.
Isn't that what work is?
We have the work energy theorem. We can get kinetic energy from it. How would I calculate the work it took to go from here to here?
Just the integral of it.
Just the integral, it's just that area. The force times the displacement gives us the work.
Yeah.
So it's just the integral. So it's just going to be the integral from x1 to x2 of our force, which in the case of a spring is k times x, times our little displacements. What's an arbitrarily small displacement going to be?
Delta x.
Dx, not
Dx.
delta x. Dx.
Okay.
Clean as day.
So constant times, so it's just k squared over 2, so 1/2.
No, k is your constant.
X is squared.
I think you meant to say x.
I didn't mean to say
Okay.
this.
So it's going to be x squared over 2 times k,
Yep.
or 1/2 kx squared at 2 minus 1/2 kx squared, x1 squared, sorry. Right?
Okay.
So here's the work that's done on a spring. And you'll notice that that is very similar to
Or equation.
your kinetic energy equation.
Yeah.
You just replace your x with velocity.
Do we have any names for this, or is that just it? Like 1/2.
That's just it. Notice that with the other one, we were talking about displacing an object.
Yes.
This one now we're talking about stretching a spring. So it's not the exact same scenario as we were talking about before.
Okay. But you solve it the same way, basically.
Well, here's how you do it for springs.
Okay.
You want to know how much work it takes to stretch a spring a particular distance, how much energy it takes to stretch a spring from one position to another position. Here's how I calculate it. So it's very similar to what we were doing with just kinetic energy. Make sense?
Yeah.
Alrighty. So let's just do an example now with springs, and then we'll get to power.
Yeah.
So, gonna have someone stand on a bathroom scale. A woman weighing 600 newtons. It's quite a bit. Actually, I have no clue. A woman weighing 600 newtons steps on a bathroom scale that contains a stiff spring in equilibrium. Oh, sorry, contains a stiff spring. In equilibrium, the spring is compressed 1 centimeter under her weight. Equilibrium meaning there's no acceleration.
Even, yeah.
So once things have evened out, yeah. In equilibrium, the spring is compressed 1 centimeter under her weight. Find the force constant of the spring and the total work done on it during the compression. So force constant of the spring, that was that K there. When we said the force on a spring, Hooke's law, force is equal to some constant times X, that K changes depending on your spring. Stiffer springs have a big K, smaller springs have a little k, but that's what they mean by the spring constant.
Okay.
Make sense?
Yeah.
Okay, so we know that she compresses it 1 spring, or 1 centimeter. So we know that our x, or our displacement in the x direction, is equal to 1 centimeter, which is 0.01 meters, right?
Yeah.
And we know that her weight is equal to 600 newtons. So we know that the work that she did, well, how's the right way to say that? When she applies 600 newtons to the spring, it compresses 1 centimeter. So we can figure out the spring constant from that.
Oh, so we're looking for the constant.
Hooke's law tells you if you compress me or stretch me this much, you should get this force. We know that if we got a force of 600 newtons when we compressed you by 0.01 meters.
Oh, that's pretty straightforward.
So now we get our spring constant, which is equal to
60,000.
6.0 times 10 to the 4, right?
There we go. Yep.
Okay, so that's our spring constant. Now, the next thing we wanted to calculate was the work that she did on the spring.
The work that she did. Okay.
Yes, and the work that she did is equal to the integral from 0 to 0.01. Started out not stretched, and it went that far.
Okay.
Times our force, k times x, times our displacement, dx.
Yeah, gotcha.
Good? K, we already know what that is, but we'll plug that in the very end. So then this is going to be equal to 1/2 kx squared. When we plug in the 0, it'll just be 0, so we don't need to worry about that. Well, sorry, let's do this first. 0.01, like that, right?
Yeah.
which is equal to 1/2 K.01 squared joules. Right?
Mm-hmm.
Okay, now we could have just gone straight to an equation that we memorized for this thing. And I already knew that when I was going to calculate this integral, I was going to get 1/2 kx squared. But if you keep trying to memorize your equations for all these things, rather than thinking about how to calculate these things, your brain's going to blow up, and then you're not going to know physics a couple years from now. Because you're going to forget the equations. If you will remember that work is just equal to an integral of force times some displacement, you'll be far better off. So this is the only thing I memorize in my head. I don't memorize anything else when it comes to work. And I also have the equation for work equal to kinetic energy memorized, but that's just because you use kinetic energy so much you can't help but memorize it. And we'll see that some. But I've never memorized something like this, even though it comes out very similar. Because why would I?
Yeah.
Because I can calculate that in 5 seconds.
Yeah.
Okay.
So it's far, far better to think about work this way than to try and memorize, oh, when we're dealing in this scenario, it comes out to these are the equations you're supposed to use. Or in this scenario, it comes out to these equations you're supposed to use. If you can figure out what your forces are, you can always calculate your work. You just calculate the integral yourself. It usually is a simple integral. So far more important that you know how to plug into that integral than memorizing these equations. But they'll give you all the equations and they'll paint them in yellow to try and get you to memorize them. Way too much work. Okay, we were calculating the work. I just need to plug into my calculator. So we have 0.5 times 60,000 times 0.01 squared. 3.0.
Nice.
Yeah. 3.0 joules.
That's the amount of work she put.
Yep, that's the amount of work she put into compressing that spring.
Even though she weighed like 600 newtons.
Even though she weighed 600 newtons.
If she
applied a force of 600 newtons over a very, 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 very small distance.
I guess it makes sense because she hardly did anything. She just got up on it, didn't she?
Yeah. It's not particularly tiring for you to step on and scale.
Well.
Okay, so you wouldn't expect it to take a lot of energy. Okay. Another example that has nothing to do with springs, but I guess, maybe it does. Let's see. An air track glider of mass 0.1 kilograms is attached to the end of a horizontal air track by a spring with a force constant. Okay, it does. So let's get our picture. How are we for time? 10:30? Did I have that going? Yes. Okay. So, next example. So, we've got a horizontal air track attached to a spring. Let me just start writing up the constants. M is equal to 0.1 kilograms. Our spring constant K is equal to 20 newtons per meter. Initially, the spring is unstretched and the glider is moving at 1.5 meters per second to the right. I'm guessing they want me to go find a picture of this stupid thing. Why don't I just tell you? Figure 6.22a. Where is figure 6.22a? That's not it, that's not it. Right here, figure 6.22a. To the right, so I'm moving away. Oh, it's so hard to say the word away. Alright, so we got our spring. and it's attached now to our glider. Remember, it's on track. Glider.
Is this the thing that blows up?
The track blows air up on it to keep it kind of hovering. Initially, so the spring is uncompressed. So this is it at its natural state.
Okay.
And initially the glider is moving this way at 1.5 meters per second. Find the maximum distance d. The glider moves to the right if the air track is turned on so that there's no friction, and if the air track is turned off so there is kinetic friction, mu sub k equal to whatever. So we're going to do it in the case where mu sub k is equal to 0, there is no friction, and b in the case where mu sub k is equal to, I think it was like 24/7. Okay. Okay, so how much is this glider going to stretch out the spring? That's what we're trying to figure out.
Okay.
How much is the glider going to stretch out the spring? Now, if we knew how much work the glider was going to do on the spring, then we could figure that out, right?
Yeah.
How are we going to figure out how much work the glider does on the spring? Well, we know it's kinetic energy right now.
It's kinetic.
Uh-huh.
What is
We know its velocity and its mass. Its kinetic energy is 1/2 mv squared.
Oh.
And we know its kinetic energy when it goes the max distance is going to be 0. So I know that the total work that the glider is going to do on the spring is equal to its kinetic energy, right?
Yeah.
But it's also going to be equal to how much it displaces the spring.
Equal to the displacement?
No, not the displacement. We also know that work total, when we're talking about springs, is equal to 1/2 kx2 squared minus 1/2 kx1 squared. We just use that equation twice. Right?
Yeah.
So the total work is also equal to this. But the spring starts out initially not stretched.
So it's just
So
the first
x1 is
part.
0.
Okay.
So its final position is given by this equation. So this is the same thing as 1/2 k, we'll just call x its final position squared. How much it stretches it.
And what are we looking for again?
And we'll call this
Trying to find
x equal to 0, right there.
The displacement goes before stop.
We're trying to find how much is the max distance it stretches the spring.
Okay.
Good?
Mm-hmm.
Okay, so now we just solve for x.
Gotcha.
You with me?
Yep.
Pretty straightforward. So we know that x squared is equal to, divide times both sides by 2, gets rid of those, right?
Divide by k.
Divide by k, so we have m over k v squared. So x is equal to the square root of, well, we'll pull the b out of the square root, so b times the square root of m over k.
What? Don't you have a v times a v?
Which is why you keep it.
Which is why I pulled it outside the square root.
Oh, I see. I see.
Okay, so that now is equal to, our velocity was 1.5 times the square root of our mass was 0.1 divided by our spring constant, which was 20. And it goes 11 centimeters.
Sounds right.
Okay.
Okay, that was the case where there was no friction.
Okay.
Now we turn on the glider and we've got to do it again.
Turn on the glider?
Or turn off the air track. Sorry. Turn off the air track and now we got to do it again. Now once again, the total energy, the total work that the glider is going to exert on the spring is the same. It's just not going to stretch it as much now because it's going to be harder to stretch it because it has to fight friction.
Yeah.
But the total work is still the same. A glider with a velocity of 1.5 meters per second only has so much energy in it. And it has exactly how much energy it has in it.
Yes.
And once you stop it moving completely, you've taken all that energy out of it.
So it's still.
So it's the same amount of energy. It's just going to give us a different displacement. So our work total is still equal to 1/2 mv squared. That's our total work.
Okay.
But now it's also equal to the integral from 0 to the x position we're interested in. I guess we'll call it x1 now, so we don't get confused by x variables in here.
Of your force times your dx.
Of our force, what is our force now? Our force now is Hooke's law. Hooke's law says force is k times x. That's the force of the spring.
Okay.
But now we also have friction.
Why are you adding that? Why didn't you
They're
just
both
subtract
pulling
it?
in the same direction.
Friction?
I thought friction opposes your direction.
Whatever way you're
So
trying.
does the spring. The spring is opposing our direction of motion.
And friction.
Imagine
No, that makes
I
sense.
have a box and I'm trying to slide it.
Mhm.
Friction's pushing that way, right?
Mm-hmm.
Now imagine I have a box and a spring attached to the wall and I'm trying to push it. Now both the spring and friction are opposing me.
Okay.
The spring and friction are in the same direction.
Yeah.
Make sense?
Yeah, that makes sense.
Okay. So adding those together and then dx. Right?
Okay.
Well, we need our force of friction. So what's our force of friction? It's equal to our normal force times mu sub k.
Your normal
Normal's the way.
normal.
Yes, static friction. Here's the equation you saw. Where n is magnitude of the normal vector.
Oh, that's right.
And in this case, it's just going to be mg.
Yes.
Let's draw a free body diagram for this thing. Okay. So for our weight, we have the spring. We have the force from the spring pulling this way. We have the force of kinetic friction pulling this way.
Mm-hmm.
We have the normal force pulling up, and we have weight pulling down. And so it's deaccelerating. It's going to stop moving.
Yeah.
Okay.
What's pushing it?
Nothing's pushing it. It just has an initial velocity.
Okay.
So it's only being pulled. It's just coming to a stop. The question is, how far is it going to go before it comes to a stop?
Yeah.
Make sense?
Mm-hmm.
Okay. So our force of friction then, force of kinetic friction, is that value right there, right?
Yeah.
So this is equal to the integral from 0 to x1. X1 is what we're looking for. Of k times x plus mg mu sub k. M times g times mu sub k dx. With me?
So it's just a bunch of constants and then x.
Yeah, so I'm going to split this into two integrals now. So this is equal to the integral from 0 to x1 of k times x times dx plus the integral from 0 to x1 of, put mu sub k first, mu sub k times m times g times dx. Right?
Mm-hmm.
And this is equal to, I'll rewrite the left-hand side. We know 1/2 mv squared is equal to these, sum of these two integrals, right?
Yeah.
What's this integral?
Just
Just
1/2 kx
k
x squared.
k x1 squared, right? Because when we plug in 0, it will just be 0.
Oh, that's right.
Good?
Mm-hmm.
Plus mu sub k times m times g times x1.
Okay.
Good? Oh, what an ugly problem. We have to use a quadratic equation. So we have x, well, let me write the coefficients of this first. We have k over 2 times x1 squared plus mu sub k times m times g times x1 minus 1/2 nv squared is equal to 0. So we have x1 is equal to negative b plus or minus the square root of b squared
That is a lot.
squared minus 4 times a times c all over 2a. Now obviously we're talking about a positive displacement, so it's going to be the plus sign there, not the minus.
Okay.
So that's one we're interested in. So plug in this monster of a formula. Just in case I make a mistake, I'm just going to store these values as numbers. So I'm just going to call this b. So b is equal to, let's see, what was mu sub k? 0.47? 0.47 times, our mass was 0.1, times 9.8 is equal to that value, store u in b. Okay, so that's our b. Our a is just k over 2. What's k? 20. So our a is just 10. 10 store in a. And our c is negative 0.5 times our mass, which is 0.1, times our velocity, which is 1.5 squared. We'll take u and we'll store u in c. Okay, so we're looking for negative b plus the square root of b squared minus 4 times a times c, and I need the whole thing divided by 2 times a, which is 8.5 centimeters, so they'll probably say 9 centimeters. No, they say 8.6 centimeters. Okay. So round it up, round it to 2 decimal places. This is 0.086 meters, which is slightly less than it was without friction. Without friction, with friction.
Oh, that makes sense.
Good?
Yeah.
Nice, easy problem. Just a bit of algebra. Nothing too hard about it. Okay. Last example problem before power. You're pushing your nephew on a swing at a picnic.
What has spring to do with it?
This is swing, no spring.
Oh, okay.
Okay, at a family picnic, you are appointed to push your obnoxious cousin in a swing. His weight is W, and the length of the chain is R. So here's where he is at rest. You pushed him some. Here he is on the swing. Pull the swing back and push on ball, same effect. This right here, they're calling to some angle theta naught.
Theta
But
naught.
it followed some arc path. You're going to push them up to some angle theta naught, I think.
Okay.
I see a theta naught. Oh, I see theta naught there, but didn't say that. You're just going to push them up to theta naught, but here's theta at the instant time. Okay, so we know that his weight, we know W, the weight, that's given, whatever it is. And let's see. Oh, and we know the radius R. Let's see, on one side.
Oh, it's one of these.
Radius R. All right. His weight is W, the length of the chain is R. You push him until the chains make some angle, theta naught, with the vertical. To do this, you exert a varying horizontal force, F, that starts at 0 and gradually increases just enough so that him and the swing move very slowly and remain nearly in equilibrium throughout the process. What is the total work done on him by all forces? What is the work done by him by the tension in the chain? What is the work you do by exerting the force F? Okay, so he's like that. You're pushing on him at the horizontal F. And your force starts out at 0 and then gradually increases and increases and increases, keeping him moving with a constant speed up.
Okay.
Okay? And then obviously there's tension here in the chain. Free body diagram for him really quick. You're pushing, here's the force that you're pushing with. Tension is this way. And then his weight is this way.
There's no normal force?
Tension. That's the same as the tension.
Okay. How is it the same as the tension?
Cut the rope. What's the normal force?
Oh, I see.
Yeah, don't accidentally double count forces. You can either count the normal force of the swing pushing up on his butt, or the tension of the chains in the swing holding him up. It's all the same force.
Okay.
So yeah, don't accidentally double count your forces. Because ask yourself, if I remove one force, did I remove one of my other forces? That should not be the case. Getting rid of tension doesn't mean that you're not pushing him anymore. Getting rid of your push doesn't get rid of tension. Getting rid of weight, etc.
I see.
Well, I guess weight does get rid of tension, technically speaking, because you get rid of gravity. Or at least part of it. Some of your tension's still going to be there because of this force. Anyways, so there's all the forces acting on him. Let's see. So calculating, not sure exactly what we're after, sorry. What is the total work done on him by all the forces, but I think we're supposed to do that something before that. So that means, what is the total work done on him by all forces? What is the work done by the tension T in the chain? What is the work you do by exerting the force F? Okay, so easy one really quick. What's the work done by the tension in the chain?
It's the sign.
0. There is no work done by tension in the chain. He never moves in the direction of the chain. The chain stays, he stays the same distance in that direction the whole time.
Does that mean the weight is doing no work?
No. His weight's definitely going to be doing work, and you're definitely going to be doing work. Tension is never going to be doing any work.
That doesn't make sense to me.
tension is always at a perfect perpendicular to how he's moving.
Yes.
So, if we say tension times his displacement times the cosine of the angle between them, what's the angle between them always?
180.
No.
90.
If it's on a then yeah, 90.
What's cosine of 90?
0.
0. The chain is never doing any work on him when he's swinging. This makes intuitive sense. When you're swinging, you never move in the direction of the chain.
No.
Your swing never moves up towards the chain. It moves up, meaning you're swinging, but you never move in the direction of the chain.
Yeah.
Your chain stays fully extended. If you move in the direction of the chain, it would contract some. That never happens.
Okay.
So no work is done by the tension force.
Okay.
That's the easy one. Okay, so let's calculate now his forces in the x direction, force in the y direction. We need to come up with a x and y that we're going to call this thing. Let me see real quick here. The motion is along the curve, so we'll do s along the curve. We'll call that distance s. So we're going to set up a weird coordinate system here where, well, is that what we want to do? Just don't want to get blown up in algebra. Well, let's just calculate the total work. The total work total, is going to be equal to, well, when we calculate that, we're going to need to do some sort of integral from some position A to some position B. We'll think about that later. But we need to do of your total force vector, the sum of all the forces. Sorry. That's just a force that is changing. This is the sum of all the forces. What should we call that?
Your force vector is the sum of all your forces?
We need the sum of all the forces, and I'm trying to think what to call the force that you push with them. What do they call that? I don't really have a good name for it, so we'll just leave it. That's so confusing. We'll just say W. Here's you pushing. Okay, we need to find the total force vector, right? The sum of all the forces.
Yeah.
Summing up this, this, and this. And then we need to do the dot product with that, with your displacement vector, where dr is going to be a small displacement from here to here, or from here to here.
Okay, I see where you're at.
This is ultimately the integral that we're calculating. A is our start position, and B is our end position.
Okay.
Okay, so first thing we need to do is calculate our total force vector. So we'll calculate all the forces in the x direction, and then we'll calculate all the forces in the y direction, and that will give us our force vector.
Okay.
Good? So all our forces in the x direction, what do we have? We'll just say that one F. I think it'll be fine.
We only need to calculate F and W, right? Or do we need to add the tension in as well? Even though the work on it is 0.
I was just pointing that out. Okay, ignore that now. We're just going to find the sum of the vectors. We're going to add up all the forces. Okay, so adding up all the forces in the x direction, we have tension is that way in the x direction, the force you exert is that way in the x direction. So we have F here minus
Sine of T.
theta, here's theta right here. So minus our tension times the sine theta, good. Now our force in the y direction, we have in that direction, we have,
Cosine T times
we'll
cosine
call
of theta
up positive. So we'll say T times cosine theta
minus his weight.
minus W. Perfect. So there is our f of x and our f of y.
Okay.
And so how am I going to calculate my dl vector? let's see, to compute the work done, F, we need to know how his force varies with the angle theta. Oh, find the magnitude of F now by eliminating T. I feel like I'm making a mess of this problem. Let's come back to this problem here in a sec. Let's move on to power, then we'll come back and do that problem.
Does this involve power?
No, this was just a force problem, but I feel like I'm making a mess out of it really quick. We can just keep going maybe. Okay, to compute the work done, F, we need to know how this force varies with the angle theta. Yes, the net force on him is 0. Oh, duh. I'm missing a completely useful piece of information. Which is equal to 0, which is equal to 0. Forgot what the problem said right in the beginning. No wonder I'm getting stuck.
Net force is 0?
The net force is 0 because he's at equilibrium. You're keeping him moving with a constant speed.
You're pushing him at a constant speed.
You're pushing him so he's moving with the constant speed. The force you're using varies. At first you're applying a little bit of force and you're applying more and more and more force as he gets higher and higher and higher to keep him moving forward with the exact same speed.
Okay? But how does that make your x force coordinate 0 then?
Because his speed in the x direction isn't changing. And his speed in the y direction isn't changing.
But it's moving.
Yeah, but you're moving.
So, initially there is some acceleration to get moving. And that happens in the very first instance. And then from there on out, you keep him moving with constant velocity.
Oh, so your acceleration is
So
0.
ignore, so you pull him back a little bit and you get him started with a little bit of velocity. Okay, now he's got a really small velocity.
Mm-hmm.
Now you maintain that velocity perfectly from there on out.
So because he has no acceleration, that means his forces are 0. Okay,
So
that
the net
makes
forces acting on him in both directions are 0. You're moving him really slowly so that he's in equilibrium.
Okay.
At all times. Okay, so from this, we're able to get our F in terms of W. Because we can solve for T in terms of W here, plug in for T, and then we can get F. See that?
Mm-hmm.
So we have, from here, we can say that T then is equal to W over cosine of theta, which gives me that F is equal to T times sine of theta, right?
Yes.
Which is going to be W times tangent of theta.
W times 10. Okay. Yep.
So there is our magnitude of F.
We're looking for the magnitude, yeah?
That's just the magnitude of F. Let's see, so we find that by eliminating T from the two equations, we obtain the magnitude of F, W tangent. The point where the force is applied moves through the arc S. The arc length S is equal to R times theta, sure. Okay, so that's ultimately the equation we're going to use. Okay, so taking this equation now, let's rewrite over here so we have some space.
Mm-hmm.
I know that the other way that I can write this thing, when we do the dot product between two vectors, that's the same thing as, so work total is equal to the integral, we'll figure out our bounds here in a second, but from some point A to some point B. We can also say it's the magnitude of this times the magnitude of this times, well, we can say it's force times cosine of the angle between them, cosine theta, times
Your distance, so your S.
ds, yeah, I want to use an s now, well, because that's a small change in s. So we're going from dr's to ds's because s is now an arc length rather than just a position vector. It would have been like the magnitude of our position vector.
Okay.
Does that make sense?
Mm-hmm.
Okay, now we know that s here, arc length, how do you get arc length if you know theta? It's just theta times r.
Yeah.
Mm-hmm.
So ds then is going to be r times d theta. R is just constant.
R times d theta, okay.
So that's the substitution we're making here. So this is equal to the integral now. And now we know what we're going to be integrating with theta. Our theta, they told us, goes from 0 to some other value, theta naught. So when we're done pushing him, that's at some angle theta naught.
Gotcha.
And so that is going to be our F, which is our weight times tangent of theta, times cosine theta, times ds, which is r d theta. Okay. Think we're on the same track. W tangent theta, cosine theta, r d theta. Okay.
Isn't sine over cosine is tan, right?
Yes.
So you can just cancel that out.
Yes. Okay. So this is equal to the integral from 0 to some value theta naught of, let me plot my constants also, so we can see that. His weight is just constant and the radius is just a constant, so we have omega times r on the outside, right?
Mm-hmm.
And then like you just said, tangent and cosine, when you put that together, you get sine of theta, d theta.
Oh, what's the integral of sine of theta?
What's the integral of sine theta?
Isn't it just negative cosine?
Is it? What's the derivative of sine?
Then it's
Cosine.
negative.
Okay, so then the integral has to be the negative, right?
Yeah.
Yeah.
Evaluated from 0
Theta naught.
to theta naught. Now, let me think. We got to plug in theta naught and then minus what we get when we plug in 0.
Which is cosine of
So
0.
we have omega r times, we can keep that factored out. So we have negative cosine of theta naught minus 1, or plus 1.
Cosine of 0 is
1.
1.
So
So it would
minus-
be minus 1.
Minus,
There's not two negatives there.
there's a negative here.
Yeah.
Okay?
Okay, let's write this very explicitly. So it's going to be negative cosine of theta naught minus negative cosine of 0.
Okay.
Yeah, I have that.
Okay. So now this is omega times r times 1 minus cosine theta. That's the total work. Now we did this way the hard way, because you can just use some basic trick to find that exact same value.
Why doesn't it tell us what his weight is and what the radius is?
It doesn't matter what his weight is, doesn't matter what the radius is. It's just given.
Oh, so we were just trying to figure that formula out.
Yeah.
I see.
So the total work is that. Now we could have found this mg. Okay, I'm like, wait, mass and gravity should come into this. So that's the same thing as mg. Just for my peace of mind.
Okay.
mg. You know, we could have found this just using a little bit of trick. And could have done the same thing without all this hassle. I think.
Okay.
Because our work total, ultimately, when you're pushing the ball forward, you're pushing at some displacement into the right,
Yes.
and then you're pushing it up some. To the right, you're not doing any work. All the work goes into the fact that you lift that thing. In other words, if I take this book and I move it right here, I haven't done any work on the book.
But it moved.
But it moved, but there was no friction or anything like that. I didn't apply a force that way over some distance. I'm doing 0 work on the book right now. If I pull on the floor and I start pushing it, now I'm doing work on the book. But all the work in the book goes into lifting the object, lifting the book.
Because you're fighting gravity.
Yes, gravity is the only thing actually acting on this thing to do any work on it.
And you're saying because the force is 0, there's no work. Right?
No work in the x direction.
No work in the x direction. Look, if I did work in the x direction, then this seems I should be able to get some energy back out of this thing. And I can't. Now I can. I did work, and now I get the work back out. If I did work on it this way, where'd the energy go?
makes sense.
Nowhere. I mean, you're thinking I sped it up and I stopped it, but imagine I'm just moving with constant velocity. I'm not doing any work on the book right now.
Okay.
The change in kinetic energy is 0.
How's that change when it's on the floor?
Now there's friction. I have to overcome friction.
So that's where the energy goes?
Mm-hmm.
Okay. But not all of the energy goes into overcoming friction.
All the work does. If I'm moving it on the floor with constant force, or with constant velocity, because then I'm constantly overcoming kinetic friction,
Oh, yeah.
right? So if I'm walking with this book with a constant velocity, I am not doing any work on the book. When I lift the book, now I'm doing work on it. So when we're pushing him on the swing, the push this way isn't doing any work. It's the push that we have to do to lift him that does work, which is why it gets harder and harder the further we push him. And we're exerting more and more and more of a force is what the problem says, so we're keeping it in equilibrium.
Okay.
Make sense? So all of it goes into the fact that we're just lifting it. So I'm saying we can calculate the total work by just calculating. Total work is just going to be his weight, mg, times how much we lift him, h, this distance.
Okay.
So we just got to calculate that h.
So the h is just what the. What is that?
What is that h? Okay. Well, the h right here, h at the bottom right here is just,
Sum of the radius.
it's all of the radius. At the bottom.
All of the radius? No, your little h.
To right here. Not here, here.
That's not your h though.
H is this distance.
Yes.
Okay. At the bottom, my total is this. And is r, and then we lift it up to this. So I'm going to calculate h. H then is equal to my total radius, r, minus this distance. Or sorry. Yes.
Yes.
This distance minus this distance. So now I just got to find this distance. Or sorry, now I just got to find this distance. Right?
Which is how high it is.
Which is how high it is.
Which is f, no, t times
So you can see
sine.
it? Let me draw a new triangle over here. So we have this. We have this. What's this distance?
Just the sine of
It's cosine of
R cosine of theta.
r. Cosine?
Yeah, remember it's to the right.
Right?
Right.
R cosine of theta. Okay.
Substitute that in for h. So this is equal to mg, factor out the r times 1 minus cosine of theta.
Okay. Oh.
So we did that a really hard way. But
So why
that's
didn't
the way
we just
this
do
one
it
did
that way?
Because it doesn't use. I don't know. I didn't write the book. It's just the way I naturally saw it to try and solve it, but I wanted to go through the way the book did it, so that way when you make reference to the example problem, it makes sense.
Okay.
So I tried to follow the book, but yeah, that's the way I normally would just solve this problem.
What did we do problem?
Okay, finally we get to power. Power, super easy concept, and nothing too complex about power. So, power by definition is equal to the change in work with respect to time.
Change in work with respect to time.
Mm-hmm.
Okay.
Change in work with respect to time. And there was another nice way to show this. I don't really like the book's way of doing it. But I'm not sure if I can remember the other nice way to do it. I think we can also see this. Let's see. So power is also equal to, so this is one way to think about it, and it's a really easy way to think about it. Nothing wrong with thinking about it that way. Let's let's think about what W is for a second. W, work is a cross product of F dot, what should we call it? Your
G.
position vector or
Yeah.
something like that. I think they typically would use S. Choose S. S. Right?
Mm-hmm.
So dW then can be found using this dot ds like that, right?
Isn't it with
That's
respect to
the-
time though?
Well, I can say with respect to a small change in position. A small change in work, we calculate with a small change in position.
I see.
Yeah.
Okay, so I can also write this as force dot ds dt
Mm-hmm.
but ds dt is
Velocity.
velocity. So this is also just F dotted with your velocity. So those are the two ways we think about power. Notice, once again, it's a scalar. It's not a vector.
What?
Scalar, not a vector. It's just a number. That's a dot product. So it takes two vectors and converts into a number. The amount of power you use isn't a vector. I say I've used this much power in the z direction. Doesn't make sense. Your electric bill, when you pay an electric bill, it's just a number. When you pay for your energy,
Yeah.
sorry, that's energy. Energy is just a number, and then power is how much energy you're using per second. Doesn't say in which, doesn't make sense to say in which direction.
Yeah.
So power is just your change in work with respect to time. So it's joules per second. It's how many joules per second you're using, which we also call watts. We represent that with a W. Watt is W-A-T-T.
There's a lot of W's.
Yeah, a lot of W's.
And then it may have just like W.
Let's see anything about watts in here. Trying to see if we typically use a capital W or a lower W. Capital W is typically how we represent. So typically we represent watts with a capital W.
How do you represent work then?
Capital W. You're going to have repeated letters a lot. But you should know when it's a unit. Because it's at the end of a number.
Okay.
Unless you have like 72 works.
72 works. So, point out something for you really quick. So you get your electric bill. When you get your electric bill, you get it in kilowatt hours. Kilowatt hours.
Kilowatt over hours?
Kilowatts hours. Kilowatt hours is what they give you. So they give you kilowatt, that's a lowercase k, so 1,000 watts times hour.
Times hours.
Yes. Or in other words, kilowatt times 3,600 seconds. And since watts is measured in joules per second,
Mm-hmm.
kilowatts is thousands of joules per second. When you multiply it by seconds, that gives you your total power usage. So energy is measured typically at your household in kilowatt hours, which makes sense because you're taking watts, which is energy per time, and multiplying it by time, which then just gives you energy.
I see.
So it's another one of those ones that can be confusing in the name. Kilowatt hours.
It's an amount of energy.
It's a measurement of energy.
A unit. Is it kilowatt hour?
A unit of energy. It's a certain amount of joules.
Is
You
it
can
kind of
convert
like
it to
miles
joules.
per hour?
Sure.
Sure.
It's a conversion factor for joules.
Okay.
So you can convert 1 kilowatt hour to joules. I'm not sure how many joules it is. We'd have to do. Is that pretty straightforward to convert? Is it just equal to 3,600,000 joules?
Oh, that's it?
Oh, yeah, that makes sense.
Yeah, I think that's it. So 1 kilowatt hour is 3.6 million joules.
What's the conversion for a typical household for the payment of that? So how much would 1 kilowatt hour equal?
But you don't pay your own bills?
gotta look at bills and look at how much energy I use. What a waste of time. Alright, so let's do simple calculation, or some couple examples with power, and then we're done.
Okay.
Each of 4 jet engines on an airplane, A380 airplane, whatever. So each of the 4 engines develop a thrust, forward thrust, of 322,000 newtons. So, talking about thrusters on an airplane. Probably won't need too much space for this. Talking about thrusters on an airplane. Not really sure how to draw the picture. Doesn't matter. The force of one of the thrusters is equal to 322,000 newtons. That's how hard one of the engines is pushing.
Okay.
Newtons. When the airplane is flying, so our velocity, v is equal to 250 meters per second. Alright, now let's just read the question out. We got everything on there. Each of the 4 jet engines on the airplane develops a thrust of 322,000 newtons. When the airplane is flying at 250 meters per second, what horsepower does each engine develop? Horsepower, I don't know how to convert to horsepower. Horsepower is also a measurement of watts. So watts to horsepower is kind of like meters per second to miles per hour.
Oh, I see.
So I have no clue what it is for horsepower, but let's figure out how we calculate this real quick.
Okay.
Force and velocity. So my force and my velocity are going to be in the same direction.
Yeah.
So the dot product between them is just going to be multiplying those 2 numbers together. Because I know power is equal to F dotted with V, right?
Mm-hmm.
This force is this much in the x direction, 0 in the y direction. This velocity is this much in the x direction, 0 in the y direction. That's one way to think about it.
So those are vectors.
This is the magnitude of the vector,
Yeah.
but both the vectors are pointing the exact same direction. So the angle between them is 0. Cosine 0 is 1. So this is just going to be equal to F times V, is what I'm getting at.
Yeah,
In
I
this
see that.
special case. Okay, so that's what it is in watts. Let me convert watts to whatever.
Horsepower.
So apparently 1 horsepower is 746 watts. So our power in terms of horsepower will be that divided by 746. So it will be this many watts divided by, well, let's try it this way. First off, when I calculate that, that will give me that many watts, and then I'm going to multiply that by 1 horsepower, capital H, lowercase p, I think, no, both lowercase. 1 HP over 746 watts. And that will convert to horsepower for me, right?
Yep.
So we take our lovely calculator, 322,123 times 250 is equal to whatever. That divided by 746 give me, you're probably going to do 108,000 horsepower. Yes. Which is roughly 108,000 horsepower.
It's a lot of horsepower.
Okay. Generates as much power, one engine generates roughly as much power as 108,000 horses.
Quite a few.
That's pretty powerful.
And that's one of the 4 engines.
What is it being
Huh?
What's it
A
powering?
plane.
That's the thruster on a plane. There's 4 engines that keep a plane going. Each of those 4 engines are generating that much power. Crazy. Okay. Last one. A 50-kilogram marathon runner runs upstairs to the top of some building that's 443 meters tall. To lift herself to the top in 15 minutes, what must her average power output be? Okay, so this girl gets to the top of the building. Her mass is 50 kilograms. So mass is equal to 50 kilograms. The building is 443 meters tall, so the height we're going to go is 443 meters. And the time it takes is 15 minutes. So 15 times 60 seconds.
Okay.
We are wondering what is her average power that she generates. So we need work divided by time. Right? And what's the work? Well, we just take
The weight.
her weight times the displacement. And that gives us the work, and we divide by the time, and that gives us the horsepower. Or not the horsepower, power. Make sense?
Yeah. But isn't power force times velocity?
That's one way to do it, sorry. We also know that power, average power, is your change in work divided by time, and your instantaneous power, by your change in time, and your instantaneous power is the derivative. Change in work with respect to time.
Okay.
So these are the typical ways that we represent power, and then this was a nice side note one to have in your back pocket to save you a lot of work and things. But here's the standard definition.
Okay.
It's just change in work with respect to time. Okay, so her work then is going to be her mass times g, which gives us her weight, right?
Mm-hmm.
Times, since she's constantly going up, then these are pointing in the same direction.
Okay.
The way that she's pushing up to overcome her weight, so we're really talking about her normal force. She has to lift up, and it's in the same direction. The way that she pushes is in the same direction that she's going to the top of the building. So we just multiply it. Does that make sense?
Yeah.
So times 443, that gives me her work. Take her work and divide it by the time it takes her, which is 15 times 60 in seconds. And we get that her average power was 8, 6, maybe, I think we had 3 significant figures, 0, 0, 0, watts.
Okay.
Now, I did something wrong. That's way rough. And I forgot my parentheses there. There we go. 241 watts. 241 watts. She's definitely not being more powerful than a horse while doing this. And 1 horsepower is 746 watts.
Oh, I see. Yeah.
Okay. And actually check it with the bug, 241 watts. Okay, there we are. That's the end of chapter 6, work energy theorem. So,
Okay.
and lecture, hopefully camera didn't die. Low battery.